look, this is a really simple model, but I think it's good enough to like explain what Creo Simulation Live is. So if we're familiar with Creo, there is a tab there called Live Simulation. And so this is directly embedded into Creo. And I'm going to do a really simple analysis on this model. This model hasn't been set up, no tricks here. So I'm going to set it up from scratch, and you see how quick and easy that can be. So if we go, okay, we'll create a planar constraint here, and we'll create cylindrical to represent all of the bolts that might be there. Okay, and you can see I just got to click a few times there. Then that's basically, that's the constraint setup. The material's got material properties which have been assigned in Creo. So I'll put a force on here, which we're going to say is, like, say 50 newtons in the Y direction. Okay, as soon as I've done that, I solve. Okay, and you can see what's happening is it sort of develops the solution over time. It sort of iterates towards the solution, but it gets there fairly quickly. Okay, it's a little bit, it is a different technology than the traditional analysis, as Alan mentioned, but you can see how quickly we get a result there. So we're looking here now at the maximum von Mises stress. So, okay, perhaps that's a little bit too high. All right, so for our design, what can we change? So we'll say, okay, maybe we can change the width of this to, I don't know, 3.5 instead of 3. Okay. Now, you notice I've just gone, I've had the simulation visible there and running, but then I've gone away and made a change. So the system then automatically starts to recalculate. So we had, 270 before, now we've got 240. If that's still not enough, we can, we can change again. So we can say, okay, now it needs to be 4.5 or something, okay? And it's really, really great for giving us that sort of understanding about what's happening with the model. I guess if you think about this model, the way it's loaded, constrained, intuitively, if that gets wider, the stress should go down. Yeah, that's okay. But in other scenarios, we might not know. And I guess the intention is here that it's meant to be a design level tool, for anyone and everyone. And sometimes, we might not understand what we're actually, a change, what influence that might have. So you can see here we've done that change. So we're looking here at the stress, but we can also look at many other things. So deformation. So how far does that deform? There's the ability for us to animate that to see, okay, and this is exaggerated, of course, but you can see that we get a potential deformed shape that shows us how our loads and everything, that's the culmination and the summation of all of our loads are coming in. And although I've kept this quite simple here, I've just done a couple of constraints. There are a whole bunch of other types of loads and so forth that we can apply. So you can see here as well some other options. Now this is, as Alan said, based purely on the GPU. If we go here as well, we have a setting which is basically a fidelity setting, which allows us to control how accurate these results are. Now, at the moment, this is just sort of set to, I guess, optimal speed versus accuracy for the demo, and this is the default setting. But if we want to go to higher accuracy, we can. It just means that time that it takes to solve increases. So I won't do that for today. The other thing we can look at as well, in some models, it can become a bit of an issue about, this is getting into more technical side of things, but how accurately our model is analyzed, and you know, we can actually start to have a look at. And anywhere areas that we've got that are really red, yeah, would be a problem. But I mean, just based on my experience, this model is working quite well. Okay. All right. That's pretty much it for the structural side. Alan, I'm not sure what your plan was for if we want me to do this, the fluids now,
Yeah,
or
sure.
go.
No,
Yeah, yeah.
now it's fine. I think, yep, we got time, so yep, that's all good.
Yeah, no, I just didn't know if you had anything else to say before that. So
No,
that's okay.
no, all good.
All right. So moving on to another relatively simple example. You know, we've got a tap set here, faucet, whatever you want to call it. Okay. Now, again, we've got the light simulation tab, but here we're actually working in the fluid mode. And so I just point out here, Alan pointed this out before, but we can add simulations of different types to the same model. So if we have, we've got a structural analysis, that's fine. We can have a fluid analysis as well. When we're doing a fluid analysis, what we do need to have is a volume that represents where the fluid is actually going to flow. Now, in this case, it's been set up, but there are tools here that we can use to actually help us really quickly and easily define that. But I'll just show you what I mean, what's been set up. So there is a volume part here. So if I just open that up, this is the internal volume of what we're actually analyzing here. All right, so where the water would be able to flow. Okay. Now, if we come back to here, if I was to select that part, you can see that it's sort of, it is sitting inside the overall solid geometry. So to set this up, again, it's pretty simple. In this case, a good option is to set a mass flow, so we know how much water is flowing through through here. Now, in this case, we're assuming, I guess, that we're turning both taps on to full or to the same amount at least at this particular rate, which we obviously would need to know and determine. I mean, if we're turning one on faster than the other, then of course we can adjust those values, but for now we're just assuming it's the same. Now, of course, one of them is going to be hot and one of them is going to be cold. So we can put a temperature condition on as well. So we can say a temperature of, let's say, 50 Celsius. And we can also put another temperature on here. Let's say it's winter, maybe it's 5 Celsius, okay? So now that that's done, only thing we really need to do is set an outlet condition, and that involves simply selecting on this surface here and saying there's a pressure. So typically in CFD and this type of analysis, you set a 0 outlet pressure, so I don't even need to type a value in there. All right, that's all I need to do is set it up. Now what I need to do is just run it. And so you can see in the graphics toolbar here, and this was there before in the previous analysis, there's a little button, and you can see that at the moment this is showing velocity, but let's quickly change it to temperature. And you can see on the left, we've got hot, on the right, we've got cold, and how that flow is sort of, you know, as the solve is going, how it's working. Now, CFD, it's not necessarily as simple as a steady state solution because things are obviously flowing, but you can see there that we get, and if we change that to Celsius, you can see the maximum is 50.018. That's potentially an accuracy setting that we talked about before, but it's, you know, very minor differential. We can also do a simulation probe, so we can measure what's happening at a point here, or we could say what's the maximum for that surface, okay? And of course, this actually is still solving and might take some time, but 30 degrees based on the geometry and all the properties of the fluids themselves, it's saying here we put a 50 degree, we put a 5 degree. You know, if you work out, if you've done chemistry or anything like that, you know, it should be on the average, the half of the value. So it should be like, but this is predicting a value. Now, of course, again, we could start to change some things that we could say, okay, well, maybe we're not changing our design in this case, but maybe we're changing a value on, if we look at here and we say this prescribed temperature, if we were to say, okay, well, now that's 75 degrees, okay? And so again, it starts to recalculate, as you can see, and you know, we're getting a different outlet temperature. Okay, so that's increased significantly. There are a few different ways we can start to look at these results. If I change it back to velocity, you can see it's where the flow is the fastest. So if you, depending on what you're looking at, cavitation, things like that, then you know, you can see, okay, well, that's where over time problems might occur. You can start to look at things like streamlines. Okay, so where, you know, where the water's flowing, you can oops, you can choose particles. Okay, and see how that's flowing. If I do change back to temperature, and what I can also do here, there is an option under here for transient mode. So this is assuming starting conditions of, you know, the temperature that I mentioned, the temperatures that we've put in. And this is looking at, okay, now we've turning it on, and you can see how it's counting up after this second. So you can see how the hot water is flowing in. The cold water is not changing things too much over here yet. And it's actually heating up all the water inside. And this is only after a couple of seconds. All right, if we set that to actually Celsius, that might make more sense. All right, so you can start to see it's taken 4 or 5 seconds. And if we were to put like a probe maximum value on that surface, we can then start to graph this and then see what happens to the maximum temperature over time. And you know, I'm sure hopefully this example does make sense to you guys, and you can start to see that it's going to take some time based on those that particular flow rate. Now, maybe the flow rate and so on needs to be adjusted, and that time would come down. But certainly the you know, what you see on screen there is, I guess, approximating reality. So
Yeah, so it's showing me why it takes so long for the hot water to come out of my taps when I turn them on.
you need to get a better hot water service.
That's right.
We'll get it in the roof. Anyway, yeah, but you know, it's, as you can see, very, very quick and easy to set it up and then to, you know, start to investigate things, what's happening.